Good day everyone, I am Manuel Maglunob of BSECE 3A and this is my activity 8 in ECE41. And I have picked 3 antennas which corresponds to the initials of my name. So M for Cassegrain Reflector Antenna, P for Yagiuda Antenna, and M for Microstrip Antenna. So let's get started. So Cassegrain Reflector Antenna. So in telecommunications and radar, a Cassegrain antenna is a parabolic antenna in which the feed antenna is mounted at or behind the surface of the concave main parabolic reflector dish and is aimed at a smaller convex secondary reflector suspended in front of the primary reflector. So here is an illustration of a Cassegrain antenna. So the parts is a horn, a parabolic antenna, a hyperbolic reflector, and focus of parabola and hyperbola. So here is another illustration or another design of a Cassegrain antenna. So there is a secondary hyperboloid, a focus, a primary focus or virtual, and the port. So the design has the specific measurements. So examples. So here is an example of a Cassegrain reflector antenna, another one, and the last one. So other designs. So in this image, we have 2 designs of Cassegrain antenna. The one is with TMCP and the other one is with RMCP. So the only difference is in TMCP, the parabola or the parabolic reflector is closed, while in RMCP, there is a small opening. And in the RMCP, the feed with LP is slightly bended. And here is a graph of a Cassegrain antenna. So it is graphed or plotted in an XYZ plane. So if you can see, there is a main reflector, a subreflector, and the frequency which is corresponding to the y-axis. And here is another graph of a Cassegrain reflector antenna with signal. And Cassegrain antennas. So Cassegrain antenna improves performance of large ground-based microwave reflector antennas for satellite tracking and communication. So it is one of the application of Cassegrain antennas. Another is Cassegrain is attractive for applications that require gains of 40 dB or decibels or greater. So both single and double reflector were designed to convert a spherical wave at source into a plane wave. Magnification factor is ratio of main reflector diameter to subreflector diameter. For a high magnification, amplitude distribution is controlled largely by subreflector, and phase distribution is controlled largely by curvature of main reflector. Advantages of Cassegrain reflectors is the ability to place feed in a convenient location, reduction of spillover, and minor low radiation, ability to obtain an equivalent focal length much greater than physical length. It introduces shadowing, which is principal limitation of its use as a microwave antenna, and shadowing can significantly degrade gain of a system unless main reflector is several of a lambda. So here is an example calculations of a Cassegrain antenna. So here is a formula: F sub minus Z sub equals F ref minus Z ref is equals to A sub over A ref. So it is a computations of the parameters of the reflectors specified by the designers are A ref, F ref, A sub, and F sub. So here is another one. So the problem is, given the 10 dB beam width, it is possible to determine required aperture radius as beam width is equal to 66 degrees over WLO over A horn. So that is the formula. So let's proceed to the Yagiuda antenna. So Yagiuda antenna, or simply Yagi antenna, is a directional antenna consisting of two or more parallel resonant antenna elements in an end-fire array. These elements are most often metal rods acting as half-wave dipoles. So it is a directional commonly used in communications when a frequency is above 10 MHz. This type of antenna is popular among amateur radio and citizens band radio operators. It is used at some surface installations in satellite communication systems. So here is an illustration of Yagiuda antenna. So the parts are, the first one is the horizontal support, and it is followed by the directors. So in this illustration, we have only two directors, but in reality, you can have as much as director as you want, depending on your needs or your applications. So we also have an insulator, a stand, a driven element, folded deep dipole, a reflector, and a clamp. So this image is the structure of a Yagiuda antenna. So introduction to the Yagiuda antenna. So the Yagiuda antenna, or Yagi antenna, is one of the most brilliant antenna designs. It is simple to construct and has a high gain, typically greater than 10 decibels. The Yagiuda antennas typically operate in the HF, or high frequency to ultra high frequency bands, about 3 MHz to 3 GHz, and covers 40 to 60 kilometers. A directional antenna system consisting of an array of coupled parallel dipoles. This is commonly known as Yagiuda, or simply Yagi antenna. And Yagi antenna is familiar as the commonest or the most common kind of terrestrial TV antenna to be found on the rooftops of houses. And advantages of Yagi antenna. First is it has a moderate gain of about 7 decibels. It is a directional antenna, can be used at high frequency, and it has adjustable front to back ratio. While its disadvantages are the gain is not very high and needs a large number of elements to be used. And here are the examples of Yagi antenna. So here's the graph of Yagi antenna. So if you can see, there is two graphs, the blue line and the red line. So the blue line represents the no feed line, while the red line represents the with feed line. So there is a slight difference, and the graph with feed line is slightly larger than no feed line. So here is another one. There is also two graphs. So the blue line is the simulated pattern, while the red broken lines are the practical pattern. So if you compare the two graphs, we can easily say that the practical pattern is slightly or larger than the simulated pattern. So here is a 3D graph of a Yagi antenna. So here is an example design of a Yagiuda antenna and the problem solving. So the problem is design a Yagiuda antenna with a gain of at least 10 dBi to receive television channel 43 UHF for a cable-ready television. So the design steps is, first, select or specify design parameters. So first in the line is desired directivity, next is the design frequency, and next is the desired input impedance. We should also select diameter D of elements and diameter D of the metallic supporting boom based on mechanical considerations and parts availability. And we should calculate design wavelength, use lambda to calculate S12 and Sij using table 10.6. values. So the formula for the wavelength lambda is lambda is equals to C over F. And on the table 10.6, we also provided that. So here is the table 10.6, which is the optimized uncompensated lengths of parasitic elements for Yagiuda antennas of 6 different lengths. So here is the table. You can pause the video to study the table. So let's proceed to the microstrip antenna. In telecommunications, a microstrip antenna, also known as a printed antenna, usually means an antenna fabricated using photolithographic techniques on a printed circuit board or PCB. It is a kind of internal antenna. They are mostly used at microwave frequencies. And microstrip antenna are also used in the fields of RFID or radio frequency identification, mobile communication, and healthcare. Basically, an RFID system consists of a tag and a reader. Generally, it uses frequencies between 30 Hz and 5.8 MHz. In telemedicine application, microstrip antenna operates at 2.45 GHz. And here are the advantages of a microstrip antenna. So it has low fabrication costs, hence can be made manufactured in large quantities, easily integrated with microwave integrated circuits or MICs. It is capable of dual and triple frequency operations, support both linear as well as circular polarization. It is low cost, less size, and low mass. And it is mechanically robust when mounted on rigid surfaces. It has high performance and lightweight and low volume. While its disadvantages, it has narrow bandwidth associated with tolerance problem, lower gain nearly 6 decibels, large ohmic losses in feed structure of arrays, excitation of surface waves, and most microstrip antennas radiate into half space, and it is relatively low efficiency due to dielectric and conductor losses. It is relatively high level of cross-polarization radiation. It is poor use feed radiation or surface waves or strips. Inherently low impedance bandwidth. It is low efficiency, extraneous radiation from feeds and junctions, and lastly, it has low power handling capacity. And here are the examples of a microstrip antenna. And here are the graphs of a microstrip antenna. So the first one, at the angle of 0 degrees, the graph is a circle or circular. While on the second one, which the angle is 90 degrees, there is a side signal. So in the second figure or second image, the azimuth plane or the 0 degrees and the elevation plane and the graph is similar to the 90 degrees. And here is a problem involving microstrip antenna. So the formula for the width of a microstrip antenna is equals to C over 2FO multiplied by the square root of ER plus 1 over 2. And the length is equals to C over 2FO over EF. And EF is equals to ER1 over 2. ER plus 1 over 2. And here is another example of calculations or problems involving microstrip antenna. So to design the microstrip feed line, the input impedance is usually 50 ohms and the gap between the patch and the inset feed or GPF usually is 1 millimeter. So that's all for my report. Thank you and God bless.